Hello, welcome to AP Daily for AP Physics C, Electricity and Magnetism. Today we're going to look at topic 9.1, electric potential energy. This is daily video 1, where we're going to explore how to find the electric potential energy of 2-point charges. I am Michelle Strand. I'm coming to you as an Einstein Fellow from Capitol Hill in Washington, D.C. So let's review. Electric potential energy, the symbol is going to be big U sub E. And it's often very helpful to compare electric quantities to gravitational quantities. So here we're going to compare the electric potential energy to the gravitational potential energy. A couple things that both require two objects. You can't have electric potential energy unless you have two charges. You can't have gravitational potential energy unless you have two objects, usually an object and the Earth for gravitational potential energy. Both are proportional to 1 divided by r. So they get smaller as you get farther away. So this is what the two equations look like. And I hope that you can see the similarities here, right? That the potential energy, the electric potential energy, is equal to K, which is a constant, 9 times 10 to the 9, times Q1 times Q2 for your two charges, all divided by R. For the gravitational potential energy, you again have a constant, it's big G. It's a much smaller constant, it's 6.67 times 10 to the negative 11. But then you take that times M1 times M2 and divide it by R. Electric potential energy is a scalar quantity, and it can be negative if you have opposite signs. So if you have a negative charge, you have to put that negative into the equation when you calculate the electric potential energy. So let's look at an example. Here, I want to calculate the electric potential energy of 2-point charges placed 1.5 centimeters apart. You've got one charge that has plus 4 coulombs and another one that has plus 6 coulombs. So the electric potential energy here is going to be, again, K, QQ over R. So K is the 9 times 10 to the 9. It's a big, big number. I've got Q1 is plus 4 and Q2 is plus 6. So I do put the signs in for those charges. And then the distance between them, I need to make sure that that's in meters. So 1.5 divided by 100 is going to be 0.015. And I'm going to end up with a very big number here because I have a big number on the top and I'm going to divide by a small number. This comes out to be 1.44 times 10 to the 13th. And it's energy, so it's measured in joules. The second part here asks, how does that answer change if the charge 2 is now negative 6 coulombs? If I plug a negative in here in this top equation, the only thing that changes is that I'm going to end up with negative 1.44 times 10 to the 13th joules. So negative electric potential energy, what does it mean for that electric potential energy to be negative? It means that I have to do work against the field to move the charge objects away from each other. Right? So think of it this way, a negative point charge and a positive point charge are attracted to each other. How each charge interacts in the electric field is the reason that those opposite charges attract. Work has to be done to stop the process and move the charge objects away from each other. So let's practice. So we're going to look at a what-if question. And what if questions are, if we have a scenario, in this case, we have two charges, they're placed a distance r apart, and the electric potential energy between the two is 50 joules. The what if pieces are, what if we change the charge? What if we change the distance? How does that affect the electric potential energy? It's always helpful for these to start off with an equation. So here's our equation for electric potential energy. We know if we keep everything the same, I'm going to have an electric potential energy of 50 joules. So the way that I recommend students, and I like to play the what if game, is that we take this equation and whatever doesn't change, we put in as a 1. What we're left with is going to be a relationship of how the new electric potential energy compares to the original. So for example, the magnitude of one charge is doubled. So if I look at my equation, K is a constant, that's not going to change. One of my charges is doubled, so I might as well make it this one. And then the other one stays the same and the distance stays the same. This tells me that the new electric potential energy is going to be double what it was before. It was 50 before, so the new potential energy is going to be 100 joules. Second one is the magnitude of both charges are halved. So I've got the K is going to be 1. I'm going to cut both charges in half and keep the distance the same. This is 1/4. So I'm going to have 1/4 the potential energy that I had, which is going to give me 12.5 joules. If I double the distance between the point charges, so K is 1, each of the charges remains constant, but now I'm going to double this on the bottom, meaning that I'm going to end up with half the electric potential energy, so 25 joules. And the last one here, I'm going to double both of the charges. So again, K is 1, 2 for charge 1, 2 for charge 2, and the distance between them is cut in half. 4 divided by a half is 8, which means again, I have 8 times the electric potential energy. 8 times 50 is going to give me 400 joules. AUP exam loves to ask these what if questions. So what should we take away from this? Know that electric potential energy is always calculated between two charges. And like gravitational potential energy, it's proportional to 1/r. And that it's a scalar quantity, so you can have negative or positive values. And the electric potential energy will be negative when the charges are opposite and will be positive when the charges are the same. Hope that was helpful. Thank you and have a great rest of your day.